Hello, welcome one more time to Environmental Economics, Economics 310. This is the beginning of week 9. Last time I misspoke by saying it was 7-8 that we're going to be doing the renewable resources. Actually, it's 8-9. So last session was for week 8 and today is week 9. For those who might be wondering, by the way, whether there's going to be a light at the end of the tunnel, and the answer is yes. And the light at the end of the tunnel, we can see it right now, and it's not a train. So after this week, let's just say in week 10, we'll have an exam. In week 11, we'll do something about pollution and the pollution policies. The pollution policies will require also lots of graphs. But after that, the last 2 weeks should be sort of a slight break, if you will, because we're going to do both population and agriculture, depending again on your background, but probably most of you have been reading or following some of the issues regarding both. And so they are really essentially descriptive. So today, this week, and not next week, but the week after that will be the last 2 sessions that do require probably much more attention to details than the rest. And the other thing also to stress, by the way, which we mentioned last time, for the sake of the renewable resources, as you all have noticed, it doesn't take really a genius in order to figure this thing out. We are stressing and emphasizing quite a lot the fisheries. So you've got to be able to do all of the problems and the models related to the fisheries, both graphically, as stated in the book and as we discussed last time, and what we're going to do today, which is to do essentially the same thing, but to show you that it's not only graphs, that there is an actual application, that if it so happens that somebody provides you with enough resources, any of you will be able to provide a decent rough estimate probably about what kind of a management policy should be followed for a particular bay or a particular fishing area. Now, having said this, what I'm going to do right now, and I've been obviously trying to work it out for the last 2 or 3 days, the problems are a little bit more sophisticated and require more math than what we assume that most of the students know in this class. And so I have worked out an example whereby it's not going to be very detailed, but it will provide you with enough of a feel for how these things work. And the sophisticated part of it, unfortunately, or the relatively sophisticated part of it, we will not be able to do, because it does require a pretty decent knowledge of calculus. So we're not going to do any differentiation or any integration in this class. We will just do really the very simple algebraic formulations. Now, we might as well get started, because really it's not going to be very long, but I just want to make sure that everybody follows me. So I'm going to write them on the blackboard or on the whiteboard. The first thing that we're going to do is that we're going to assume that these are the equations for the model. The first equation, write it down here then. The first, okay, right. So the first equation is going to be the following. I'm going to be, and maybe I will try to just keep them on the board so that I wouldn't have to keep writing them. So maybe if I will start right from the edge, I can start from here, I guess. Yeah, here we are. The first equation is dB, and this board right now is wet, and so it's going to take it a minute. We're going to say it is D, oh my goodness. I'm sorry, just a second. dB over dt. That's to say the change in B with respect to a change in t being time. So it's going to be equal to R B into 1 minus B over K. B is the biomass. Now again, since I don't have time, a place to write this, so you write this thing down. B is biomass. K is the carrying capacity. So think one more time in terms of the diagrams that we drew last time. So the carrying capacity is K, and B is the biomass, any of the levels of the stock prior to getting to the carrying capacity. R is the natural rate of growth of the population, of that particular fish population. So notice, by the way, almost immediately, if there is absolutely no fishing, how much is the change going to be in the biomass? It goes without saying that it's going to be 0, because then the biomass is equal to the carrying capacity. So it will be 1 minus 1, which will be 0. 0 times this will be 0. Whenever the biomass is less than the carrying capacity, then there's going to be a rate of change. Right? So this is we're going to call equation 1. Now let me call equation 2 the harvest or the yield. I'm going to use H. So H, I'm going to express it right now in terms of a Q, F, B. B, again, is the biomass. F is the fishing effort. Some books will call it E. And Q is what is known as the catchability coefficient. So really all what it is that it's the fraction of B that is caught by each F. So notice the logic behind it is very simple. All what we're saying is that you have a particular quantity biomass. Each fishing boat catches 0.00001%, and you have 1,000 boats, so how much have you caught? It will be 1,000 times the 0.001 times whatever this population is. And so you will get the harvest. The other thing that we're going to do right now, which I'm going to call 3, is to assume, again, if you still remember the diagram that we drew last time, at the points of equilibrium, that's where H is equal to the change in the population. That is what is known as the sustainability, right? So it's sustainable, the yield, whenever the harvest is equal to this. That's to say you set 1 is equal to 2. By setting the first equation equal to the second equation, you're gonna get the following. Are they all seen? Yeah, okay. So you set this, so you get H is equal to RB into 1 minus B over K. Now all that you have to do is go ahead and regroup. I don't know whether I want to do all the regrouping. We can do 4 or 5 different regroupings, obviously. But ultimately, what we're going to do, we're going to find out that this, I mean, I'm going to call it B sub E, the biomass at equilibrium, that's to say the biomass whereby the harvest is sustainable, is going to be 1 minus QF over R into K. Four, let me see if I can write 4 here. I think I'm going to have to eventually erase it, looks like. So 4, I'm going to assume that I'm going to right now look at H at equilibrium. But H at equilibrium really is going to be equal to the B at equilibrium, right? Otherwise they won't be at equilibrium. So it's going to be QFK into 1 minus QF over R. So as you can probably see by now, this is really all what is going to be required to do a problem. We're going to do a problem in a minute. But you'll be able to calculate what's going to be the change using 1. What's going to be the change in the biomass? You'll be able to calculate or to have a function for the harvest. You can set these equal to each other in order to have equilibrium. And at equilibrium, what is it you're going to find out? You'll find out that there is a particular biomass that is going to yield a particular harvest that is sustainable. And by doing all different variations, like what we did last time by looking really at all of these diagrams, you'll be able right now to substitute in, given certain information, in order to calculate what is going to be the fishing effort. Notice, unfortunately, I have to erase in a second, but notice what we're going to do. We're going to be able to calculate the fishing effort whenever we have an open access. We're going to be able to calculate the fishing effort whenever we are at MSY. And we should be able to calculate the fishing effort at economic efficiency. Unfortunately, we're not going to be able to do that precisely because it requires some more equations, and I don't want to throw more equations at you. But it becomes very obvious what is it that we're trying to do. It's very similar. The conclusion is the same as the one that we spoke about, 6 weeks ago, I guess, when we were talking about open access of a particular bay and the number of fish that will fish the bay and what have you. This is really saying the same thing, but right now it's not only open based on a hypothesis. It is really, we're talking about actual figures, and you can find out how is it that it is going to work. Now, if this is, I'm going to give you enough time to think about it for a second, and I will go ahead right now and erase this, if it does erase, in order to give you an actual numerical example. If you still recall we're going to do one numerical example to show how all of these things work, and they should work exactly according to the model that we have done before. So what's going to be my assumption? While I'm doing this, let me give you the exact figures and then we'll put them back on the board. Let's assume that we have a fishing bay and that the carrying capacity is 50 million units. I know, 50 million tons, 50 million pounds, 50 million fish, whatever, 50 million units. I'm going to assume also that the R, the intrinsic rate of growth of the population, is 0.4. So notice what is it that we are saying up until now. We're saying that the intrinsic rate of the population, R, again it's not showing, oh my goodness. Okay. Okay, here we go. So the intrinsic rate of the growth is 0.4. And what did I say? I said that K is 50,000. Yeah, here we are. And so K is 50 million. And that Q, one more time, what's Q? It's the catchability coefficient. So it's the fraction of the biomass that is caught by each fishing effort given that particular biomass. So as the biomass changes, things are going to change, but however, we're going to take this to be constant in this case. So we're going to say that Q is equal to 0.0005. So notice, R is 0.4, K is 50 million, the catchability coefficient is 0.005. Now, all of this is in order to introduce right now some more economics. So we're going to assume that we know the cost. So the cost for every boat, for every fishing effort, is 50,000. Now what's important for you, by the way, to remember, or to never forget, is that you assume that this is all costs. It's fixed cost, it's variable cost, it's opportunity cost. All costs for one fishing effort is 50,000. So if we have 10 of them, it will be $500,000. If we have 100 of them, it will be 5 million, and so on and so forth. But this is total cost. Everything is taken into consideration. The fishing boat itself, the labor, the engines, the nets, the everything. Then we need one other thing, which is how much are we going to sell the fish at? And so we have a price. And let's assume that it's $10 per unit, whether it's a pound or a ton or a fish or whatever it is. So it's going to be $10. So if we have all of these things right now, what can we do given the equation that we have just shown? The first thing and the easiest thing, and I would expect all of you to do it, by the way, I don't want to keep repeating this, but you've got to be able to do it, is the easiest is to look at the MSY. The MSY, we know by definition from the shape of the diagram, if you still remember, that the MSY is half of the carrying capacity. So the MSY in this case is going to be 25 million. No, not the MSY itself, but the biomass for the MSY. This is the biomass at the MSY. It's going to be 25 million. So if I plug what I know right now into the first equation, so plug into the first equation that we looked at earlier, what do we get? Let me put the equation, although this thing isn't erasing very properly, but let me just put the equation one more time so that you will be able to follow me better. We're saying, if you still remember, that the change in B with respect to time is going to be RB into 1 minus B over K. So at MSY, what's going to be the change in B right now? It's going to be what? 0.4 times 25, which is 10, times 1 minus a half, which is a half, so it's going to be equal to 5. Right? So at MSY right now, given that we know the biomass, given that we know obviously the R and the K, we can immediately calculate that the change in the biomass in the population is going to be 5 million every year. Which means what, by the way, by definition? It means that we can go ahead and harvest 5 million every year sustainably, forever. Every single year we'll be able to go ahead, if this is a rate of growth per year. It might be, by the way, a rate of growth per month or per 2 years or per 10 years, but I mean per unit of time. So this will be able to be done sustainably forever. If we have calculated this, what else do you think you need to do right now? Well, you need to know how many fishing efforts is it going to take in order to harvest these 5 million. So you go ahead right now and you plug into the second equation. And if you still recall, the second equation was that what? H is equal to, what the symbols did I use? QFB. So H is equal to QFB. Now notice, by the way, right now, that you have, you know the B, at MSY the B is 25. You know the Q is 0.005. F is the unknown, but you know H. How do you know H? Because the population grows by 5, it's going to be sustainable, so it means that your harvest is going to be 5. So all that you have to do over here, and I'm trying to save space and time, say 5 is equal to 0.005 F times 25. You will be able, therefore, to solve for F, and you'll find out in this case, therefore, F is equal to 400. So notice what we've done so far. We're saying at MSY, we can catch every year 5 million tons, 5 million pounds, 5 million units, using 400 fishing efforts, given that we know what is the cost per fishing effort and we know what is the Q. And obviously we're going to be able to find out whether this is profitable or not by plugging into the P. But it's not enough to know the MSY. What else would you like to know? You will be able to do, as we suggested earlier, the open access. So at the open access, we will do really essentially the same things. there is only one more formula that I want to add, which is, just to make it simple, B, the biomass at open access, is equal to C over PQ, and we're not going to prove it. I mean, I could prove it, but it will take us another 15 minutes or so, and most of you will probably not remember the details. So you're saying that open access, the biomass is C over PQ. Now, if you go ahead and you plug in, because I know the C, I know the P, and I know the Q, right? So what is the biomass then? The biomass is going to be, in this case, 3.2. No, sorry, wait a minute. The biomass is going to be 10. I'm sorry. The biomass is going to be 10. I thought 3.2 is a little bit, it's too low. So it's 50 over P, which is 10 times Q, 0.005. So really, it's 50 over 0.125. No, over 50 over 0.005. And so you will wind up with 10 million, for example. So notice right now, again, think in terms of the diagrams that we drew last time. Maybe I should put over here a rough one. So the carrying capacity is 50. The MSY, the biomass, will be 25. And we're saying right now for the open access, it's going to be only 10. So we're really going to be able, we're really going to exploit this particular fishery. Now, in order to have a biomass of 10, now we'll be able to calculate the H. I'm going to erase these, if you don't mind, so that we can finish this. Now, let me tell you again all what is going to happen. Given right now a biomass, what do you think that you need to calculate? You want to find out what is the sustainable harvest at that level of the biomass. So in this case, we do exactly what we have done earlier. The biomass is 10. Given that biomass of 10, you'll be able to go back and plug into one of the earlier formulas about the harvest, and you'll find out in this case that the harvest is 3.2. So if you've written these things down, or if you remember what we've said over the past 15, 20 minutes or so, you'll find out that at the level of MSY, the harvest was 5. At the open access, the harvest is going to be 3.2. What else is important is that the biomass at the MSY was 25. The biomass at the open access is going to be only 10. And it's going to follow, as you might imagine, that the calculations for the fishing efforts are going to change also. So you'll find out that the fishing efforts for open access, F is going to be 640, while for MSY, F was 400, right? B over here, so let's just write all of these things down. B over here was, what did we say, 10. B over here was 25. The harvest over here was 3.2. The harvest over here was 5. Now, you could take this, by the way, one step further, and that is to do the economics. Profits are total revenue minus total cost. Revenue is nothing but P times H, and the cost is the F times the C, right? So let's do a very quick one. At open access, what's F? 640. What's C, if you still remember, it was 50,000. So 640 times 50,000, 0, 0, 0, remainder 2, 32 million. Right? Now, what about revenue? The revenue was the harvest. What was the harvest in this case? 3.2. So total revenue right now is going to be 3.2 times 10, which is the 32 million. And the 32 million implies then zero economic profit right now, right? Because the cost is 32 million and the revenue is 32 million. And this is why we abuse, because there are no economic profit. At MSY, by the way, there are economic profits, because at MSY, what are you going to do? You're going to find out that your revenue is 5 million times 10. So it's going to be 50 million, while your cost is going to be 400 times 50, which is going to be 20 million. So your profits are going to be 30 million. So that's the difference. If we were to go ahead and do the economic efficiency, by the way, you'd find out that the economic efficiency would require even more fishing efforts. I'm not going to do it, but let's assume for the sake of the argument more than the MSY. So maybe 450. And the yield is going to be less. So maybe the yield is going to be 4. But in this case, we'll find out that the economic effort is going to be a little bit more profitable than the MSY. And that's why the MSY is used very often as a yardstick in order to try and manage fisheries, although it's not the most efficient. But it definitely is way superior to an open access. There are formulas, as I said, I don't want to give them to you right now because really it's a question of time, of how is it that you find the F under economic efficiency, and how is it that you will find also the harvest under economic efficiency. I mean, I did them for this example, and you'll find out in this example, for those who are interested, the profits under economic efficiency would have been 32 million instead of the 30 million under the MSY. Before we leave this and call it a week, I would like to probably say a few more things, and again, I'm not going to stress the math because I know that probably many of you don't know it. But what is another way, by the way, of trying to attack this problem? I would hope that many of you, especially those that are economics majors, are already thinking in terms of a production function. A very popular way of doing this, and it can be done, but as I said, it's a little bit more sophisticated, so we're not going to do the detail, but I want to mention it at least so that all of you would get an idea that there is another method, and the economics majors will be able to apply some of their previous knowledge. What is a Cobb-Douglas production function? You speak about the output being determined by a number of inputs. So you say output is a function of, maybe the most popular was what the two-factor model, labor and capital. In this case, you could say that the output is a function of the fishing effort and the population, the biomass. And you'll be able to do the exact calculations that you had done in your traditional model to be able to show that ultimately there is going to be a set of conditions that must be met, if you're going to just limit it to only two factors, whereby the marginal productivity of one is equal to the marginal productivity of the other. And it can always be shown, the very simple thing about the Cobb-Douglas production function is that the marginal productivity of one is always equal to the power to which it is raised times the average productivity. So if you're saying that output is a function of labor and capital, and you're saying therefore output is equal to A, L to the alpha, K to the beta, then the marginal productivity of labor, that you differentiate with respect to labor, it becomes nothing else but alpha over output over labor. And the marginal productivity of capital is going to be beta times the output over the capital. That is to say, the average productivity of capital. Now, unfortunately, since we don't know how to do any of these things, at least we're assuming that we don't know how to do them, so we're not going to integrate, and we're not going to be able to differentiate, and so we'll not be able to solve any of these problems whereby we're going to be maximizing the difference between total revenue and total cost in order to find out that economic efficiency. But we have drawn a diagram before, and that diagram applies 100%. The diagram that we drew the first time that we met this particular issue. And we drew it also last week. That's to say, you'll find out that if open access is 640, then probably economic efficiency might be 320, and the MSY is 400. Given linear functions, without doing any calculation, I know that if 640 was open access, as it was in this case, then economic efficiency will have to be 320. Why? Does anybody know the answer? If you know the answer to this, then you've really understood most of what we've been talking about for the past 4, 5, 6 weeks. Because in an open access, you look at the equality of the marginal cost with the average revenue, while economic efficiency, it is the equality of the marginal cost with marginal revenue. But if marginal cost is linear, is a straight line, is constant, then if given an average revenue that is also linear, such as a demand curve, the marginal revenue will bisect the distance between the demand curve and the y-axis, and so it must be exactly in the middle. So if one of them, the equilibrium is 640, the other one must be 320, and so on and so on and so on. Okay, so do read the 2 chapters about forest and water because we need just to make sure that you are aware of the basic descriptions that we speak about whenever one is talking about one of these issues. However, the precise models that we're really going to be interested in would be those that are limited to fishing. Okay, so with that, I will see you next week. Bye-bye.